time being assume that we have a homogeneous Markov chain to make things simple so that I can explain things easily. So I have some initial distribution pi. And the transition probability matrix P. So pi gives distribution of x1. And how do I describe? So this pi will be viewed as a row vector. Okay, so let's say pi is something like p1, ps. S is the size of this test space. So how do I describe the distribution of x2? Using this pi and p. Those of you who know the Markov chain should be able to tell me immediately. And like that I will get pi times p square, like that. So pi is a row vector, p is a matrix. So p is a matrix of dimension s cross s, right? So these matrix multiplications are all perfectly all right, okay? So like that you will get the distribution of various things. Now what is the fundamental result that you have learned in Markov chain? That something happens as we go on computing these elements of this sequence, pi p square, pi p cube, pi p to the power 4, like that. Something happens. What happens? It converges to something under some condition. What is the condition? Those of you who know the Markov chain, okay, do you remember the conditions? If there is stationarity, then all these things are going to be same, right? If pi is such that pi p equal to pi, then this pi p square, pi p cube, all of them will be equal to pi. Suppose that is not the case. Still something happens. We know that, right? And that requires some condition on the transition matrix. What is that condition? Idempotent. Now, something in terms of the behavior of the Markov chain. Anybody remembers this condition that will give you the convergence of the transition matrix? If it is doubly stochastic, then something happens, but let's say that that is not the case, okay? But something, is it always true that this pi p to the power n will converge to something? Is it always true? That's not true, right? So there are some conditions, okay? So what is the condition? So when will it converge to a proper distribution? So you know these conditions called irreducibility of a Markov chain or aperiodicity of a Markov chain. What is meant by irreducibility of a Markov chain? Can somebody give me the definition?
You can move to any state from any state.
So from any state you can move to another state in finite number of steps. So what does it mean? So if you want to say the same thing in terms of the matrix P, what would you say? So take any pair I and J. I is a state, J is another state. So corresponding to I and J, there will be entry in the transition probability matrix, because that will be the transition probability from the state I to state J. So Pij. So how do you state irreducibility in terms of the matrix P?
Pij is greater than 0 for Pij in n step.
So that means that if I take the matrix P, there is a power of that matrix P such that the ijth entry of that nth power is positive. That means in n step I can go there. Okay. Now I will make something even simpler for you. Okay. For our today's discussion, I will take my P matrix to be a matrix with all entries positive. That will make it a chain where when I can travel in one step to any other state with positive probability. And that also makes it aperiodic. What does it mean, aperiodic? How do you define aperiodicity in general?
GCD of number of steps in which I can move to state J from state
Yeah, so that's I say that complicated definition. Okay, what is the simpler version of or simpler definition for aperiodicity? That you will always get a power of P where all the entries are positive, right? So it's like there is an n-step transition where all the entries are positive. Okay, so we will make things simpler. We will say assume that all the one-step transition probabilities are positive. Okay, now then something happens. What is it that happens? So these two conditions. So let me write down. So usually when you study books on Markov chains, they will say the Markov chain is irreducible, the Markov chain is aperiodic, but I will not do that. I will say my transition probability matrix is irreducible, the transition probability matrix is aperiodic, because at the end of the day, it is a property of the transition probability matrix, isn't it? So somebody who doesn't understand probability understands what is a matrix and what is a transition probability matrix. What is special about a transition probability matrix? If I am given a matrix, how do I check if it is a transition probability matrix or not? What are the conditions that it satisfies? Sum of the rows are 1. That's right. Okay, so nothing else, right? If I am given a matrix, if all the entries are non-negative and sum of the row is 1, what is it called? It's a stochastic matrix. So let's say I have a stochastic matrix. And if the stochastic matrix is such that all the entries are positive, then I have a irreducible aperiodic transition matrix. Okay? So let's assume P is totally positive. So I'll use this notation. Okay? This is just a notation. It means that all the entries are positive. Okay? So that means P is, so these implies P is irreducible and aperiodic. And then something happens. So I take any initial distribution pi and I keep on calculating this pi pn, then something happens. What is that? Or forget about pi. Suppose I have this transition probability matrices Pn. So for every n, p to the power n is also a stochastic matrix, so it's a transition probability matrix. So if I keep on taking power and let n go to infinity, what happens to this matrix as n goes to infinity? And somebody describe what happens to p to the power n? For a matrix which is aperiodic and irreducible like that. That's the fundamental result in Markov chain. So if you have studied Markov chain, you must know that result. Anybody knows what will happen? So as you keep taking power, its rows all become same. And they all become something like a probability. Why something like that? They all become a probability distribution. And it so happens that that distribution is really the stationary initial distribution. So this p to the power n will converge to a matrix which takes this form something like, let's say, I use pi for that, let's use theta for that. So they all have the same row theta. So this theta is equal to some q1 qs. What does it mean for a Markov chain? Now, it's like for the time being, I had forgotten that I'm dealing with Markov chain. I was just talking about matrices, right? I have a stochastic matrix. I keep on taking its power, and in the limit, it becomes something like that. That all its rows become near equal in the limit, and each one is a probability vector. They add up to 1. The entries add up to 1. So if I take this is going to be theta. How do you prove that? Can somebody give me a quick 30-second proof? Why it should satisfy that condition? Just look at the structure. It should follow from there, isn't it? You have all these rows same, so if you multiply by theta on this side, what will you get? You'll get theta. Right? So that will happen in the limit. So this will go to this. But why it will happen for P? Okay? You think about it. So in the second half, I will expect an answer from you. Okay? So this is actually the stationary initial distribution, or as they call it, the invariant measure. Okay? Now why this happens? So in the theory of Markov chain, you learn a proof for this, and I will give a very quick and elegant proof which doesn't require any knowledge of probability, and you can just do these things using the knowledge of matrices.